So now we share the presentation. This one here, where are you? Sorry guys. I am lost. The presentation should be this one. Transcript. Okay, very good, guys. So we are presenting. So last time we did the least square decomposition or the least square fitting. So sort of we finish that part, right? We finished this idea that we were interested in matrix inverses. In order to solve matrix indices, we were looking at system of equations, the notion of invertibility, Gaussian elimination in order to find the inverse of a matrix. And now we are moving from this, let's say, this point of view of matrices, right? This use of matrices, this set of operation on matrices, and want to move more toward PCA, right? So PCA is principal component analysis. It's built on SVD, single value decomposition. So we need to introduce the notion of positive definite matrices, okay? And this builds upon the previous notion, but it's sort of something different. So PSD matrices are very, just a second, I have to go into presentation mode. I don't know why I exit the presentation mode. Okay, good. So PSD matrices, they are a beautiful mathematical object, and they are not too obvious to describe at the beginning, and then you slowly build an intuition of what a PSD matrix is as you use it and as you see its properties. Okay, so there are a few equivalent definitions of a PSD matrix. One is that it's a symmetric matrix, square, so n times n, and a matrix is it's a symmetric PSD matrix if X transpose A multiplied by X is greater or equal than 0 for all X's. Okay, so this X transpose A has this feeling of a square, right? Of elevating, taking the vector X to the power 2 into some coefficient, into some projection A, let's say. Okay, then a symmetric matrix A, it's positive semi-definite if X transpose A times X is greater than 0. Okay, so there is positive semi-definite, means that it's possible that it's equal to 0, this X transpose A times X. If it's only positive, if we call it positive definite, then X transpose A is greater than 0. Okay, and the set of matrices A for which this hold, it's called the set of positive semi-definite matrices or positive definite matrices. Okay, so here there is a little bit of misuse of the term. Okay, meaning that when people talk about positive semi-definite matrices, they most often refer to symmetric positive semi-definite matrices. Okay, so a matrix could be positive semi-definite without being symmetric, and some people use the definition not implying that the matrix is symmetric, and but these authors, right, they tie in the definition of positive semi-definite with being symmetric. So whenever you encounter these matrices in a professional setting, right, and you're looking up some theorems and you are, let's say, you're trying to use some sort of function, some packages, blah blah blah, whatever it is, remember that there is a little bit of disagreement on the definition. There is a bit of implicity in the definition. Some people mean that the PSD matrix is assumed to be symmetric, and some other people, usually the more mathematically inclined people, they do not tie the symmetric property with the PSD definition. Okay, good. So then what we can do is that we can explode this X transpose A times X into a row time column definition, and you see here, right, that this idea of a square term, this idea of a quadratic term, takes a little bit better form, right? So the diagonal elements of the matrix A are multiplied by xi squared, And then the element in position ij is multiplied by xi and xj, and then there is a 2 in front, right? So it has this quadratic feeling. That's why we call it a quadratic form. Good. So there is the matrix A. Notice that it's symmetric, and there is an unknown element A. So the question that we want to answer, let's say, is if somebody fixes for us the elements of the matrix big A to be these ones here, what will be the set of the small values of the value of the small a, the lowercase a, such that this is a PSD matrix. So what we do is that we plug in the definition, and we see that from the quadratic equation, we get that we have two zeros, one for a equal to 2 and one for a equal to -3. And then we remember our system of inequalities. So we know that the matrix is not positive semi-definite if a is less than 4, and it is positive semi-definite in the interval between 2 and -3. Okay. Okay, good. So the matrix A is positive definite for a greater than 4, and for all non-zero values of x, and it's positive definite but not positive definite for a equal to 4, and it's not positive semi-definite for a less than 4. Okay, good. So every positive definite matrix A is non-singular. Okay, so as we said, there are multiple equal definition, and so what we can say for sure, one of the equivalent definition is that it involves singular values. We haven't defined them yet, but for sure at this stage you can say that a matrix is positive definite if A is non-singular. So if there is a solution for the equation AX equal to 0, this means that X transpose times A times X is equal to 0, which means that X is equal to 0. Okay, so the two things are equivalent. Every positive definite matrix A has a positive diagonal element. Okay, so this can be seen as follows. So we know the equation is X transpose A times X equal to 0. So if we set X to be one of these unitary vector, right, that has only a 1 in position I, and we call this vector A of I, then A of I transpose A multiplied by A of I will extract the diagonal element of the matrix A in position II. Okay, and so this means that the positive semi-definite matrix has to have a diagonal which is composed of positive elements. And every positive semi-definite matrix has non-negative diagonal elements. So instead of having, if we want to have positive definiteness, then the elements must be greater than 0. If we just want positive semi-definiteness, then they have to be greater or equal than 0. A little bit of repetition here, but you understand the difference between semi-definite and definite. Very good. Ooch, sorry, guys. So let's discuss now the Schur complement. This is something that I think you've seen also when you saw the definition of a determinant during your high school days, which are not so far away as my high school days. So let's say that somebody gives us a matrix N. We can do a partition where we extract the element in the first position of the diagonal, followed by the first row of the matrix, then the first column of the matrix, and then all the remaining elements. So we say that the Schur complement of A is defined as the n-1 times m-1 matrix, which is equal to this lower quadratic term A from 2 to n, comma 2 to n, minus 1 over A2 to the n1, A transpose 2, n to 1. Okay, so this is the same definition that you have for a determinant, right? So if you remember your high school days, how you define the determinant, there is a recursive expression of the determinant that involves the Schur complement. So I assume you are somewhat familiar with this. So if A is positive definite, then S is positive definite. To see this, take any x different from 0 and define y to be equal to this expression there. Then if we say x transpose S times x is equal to this form, and this is greater than 0 because A is definite. Okay, So you see that the matrix S has this definition. So it's just applying the definition in this case. Okay. So because in order to the element A11 is greater than 0 because it's in the diagonal of a positive semi-definite matrix. So everything turns out to be okay. So we say that positive definite matrices are non-singular. If A is positive semi-definite but a non-positive definite, then this is singular. It means that at least one of the eigenvalues is equal to 0. To see this, suppose that A is a positive semi-definite but not positive definite. Then there exists a non-zero x for which x transpose A times x equal to 0. And since A is positive semi-definite, then the following function is non-negative. So what we do is that we take the eigenvalue equation, right? X minus t times A times x, when t is a scalar, and we devolve to the quadratic equation. And then we have that 2t norm of A times x squared plus t squared x transpose AQ times x is equal to this f of t. Then this must be greater than 0 for all t. Or if and only if ax is equal to 0, so there is an A times x which is equal to 0. Okay, so there exists a non-zero x for which ax is equal to 0, so A is single. Okay, very good. So let's see some examples of this. Yeah, so resistor circuit. This is how you write the current, like Kirchhoff's law. Very easy. So in order to solve Kirchhoff's law, we have that x transpose A times x is equal to y transpose times x. And this is the power delivered by the source and dissipated by the resistor. So this is the first one of the Kirchhoff's law. Don't ask me, guys. I haven't done Kirchhoff's law in a time. And the power dissipated by resistor is positive unless both currents are 0. So we are saying that x transpose A is equal to this equation. This must be equal to 0. And x transpose A is equal to 0 if and only if x1 is equal to x2. And if you remember, x1 is this object, s2 is this object, and so the currents, whatever, they must equate according to this equation. Good. So now let's discuss a Gram matrix. So let's say that we have a matrix B. Then we define the Gram matrix of B as B transpose B. Okay, so every Gram matrix is positive semi-definite, and this is sort of easy to see because we have x transpose A times x. This is equals to B transpose to x transpose times B transpose that multiplies B times x. This is corresponds to the definition of the Euclidean norm, right? The L2 norm. So Bx times x is greater than 0 by the definition of the norm. Okay, so yeah. So you remember the properties of the norm, right? So the norm is always greater than 0 and is equal to 0 only if x is equal to 0. So a Gram matrix is positive semi-definite if the norm is defined to be greater than 0. Okay, so of course you have to exclude the vector of all zeros. In other words, B has linearly independent columns. Very nice. Now let's discuss another example of these matrices. So we can take a graph Laplacian. So we have a directed acyclic graph. No, this is a cyclic graph. So we just have a directed graph. And for each node, okay, we construct this matrix, which is a B times B matrix. So in the first column, we put we put a 1 if there is an edge j that ends in vertex I. We put a -1 if there is an edge in j that starts at vertex I. Okay, and then we put 0 otherwise. So for example, here we have the node 1. Okay, the node 1 is in position 1, 1, and we see that there is an edge that starts at j and ends in vertex I. So we see there is a vertex that starts in 3 and ends in 1. This corresponds to this +1. Then we have a -1. So this is a reverse edge. So leaves 1 and goes to 2. And then we assume that there are no self loops, so that we don't need to and at most one edge in between any two vertices, right? So we don't allow multiple edges. So this corresponds to a graph Laplacian. Then the positive disseminated definite matrix A is equal to B times B transpose is called the Laplacian of the graph. And this corresponds to the, of course, B times B transpose from the previous slide. And this corresponds to this property A as the following property. So in position II, so on the diagonal, you have the degree of the vertex, so the number of edges that leave, the number of edges connected to the node, regardless of the direction. And if we are in position I minus j, then two vertices are adjacent, and otherwise we have a 0. Okay. Very good. So this is the matrix A. You see that node 1 has degree 3, and the vertices that are adjacent as 1, 2, and 3. And so the only one where we have a 0 is 2, which is not adjacent to 4. And you see that this is adjacency does not consider the direction of the edges. So this is a symmetric matrix, as you would expect by construction, right? Okay, so recall the interpretation of a matrix time vector multiplication with B transpose. If Y is a vector of node potential, then B transpose Y contains the potential differences. And if we take Y transpose A times Y is equal to Y transpose B, B transpose Y is the sum of the square potential differences. And this is called the Dirichlet energy function associated with a graph. So this was a previous example that we had on graph. And so you can get the Dirichlet energy from the previous graph. Okay. Then what we can do is that we can have a weighted graph Laplacian. So now we associate the non-negative weight omega to a certain edge k. This corresponds to, yes, to a more general version of the graph, right, where you go beyond connectivity and you also put some weights on the edges, so you can say, you can express what is the influence of a neighboring node over a certain node. So then the weighted graph Laplacian is the matrix A, which is B diagonal of omega times B transpose, where diagonal of omega is the diagonal matrix with vector omega and its diagonal. And then if you look at the matrix A that we could construct from the weighted B, then we say that on the diagonal we have the sum of the weights associated to each edge incident on a certain node. And then we have this the minus 1, which is the weight of the connects to adjacent nodes. Okay, and this is the conductance matrix of the resistive circuit omega k. Guys, I haven't done circuit theory in a long time, so I assume that you know more about this formulation than me. Okay, now Cholesky factorization. So what turns out from the math is that every positive matrix A, which is square, can be factorized as A is equal to R transpose times R, where R is an upper triangular matrix with positive diagonal elements. Okay, so this is nice. The complexity of computing R is 1/3 n cube flops. Okay. And R is called the Cholesky factor of A. It has the meaning of the square root of a positive semi-definite matrix. Okay, so it turns out, right, the positive definite matrix can be decomposed as the product of as a sort of a square form of an upper triangular matrix, and then it gives a practical method for testing positive definiteness. So let's see the Cholesky factorization algorithm. So we start with this block formulation, which comes again from the from the definition of determinant that you guys have seen before. So we apply this recursively. Okay, so we have this. If we have this formulation, then we know that we can express this as this product, right? So this is the matrix R. This is the matrix R transpose. So you see that the row becomes the column. Then we express this. So here we have the R1 square, and we have the sum of the matrix time vertex components that we have in this block decomposition. And the off diagonal, we have a scalar that multiplies the row vector and a scalar that multiplies column vector. So now we want to solve for R11, which is the scalar that we have in the equation. And of course, our R11 must be equal to the square root of A11. when you see a square root, your little engineering antennas go up, because of course square roots only exist if we take a positive square roots without getting imaginary numbers into the mix exist only if A11 is positive, but we said before that the positive semi-definite matrices, they have positive entries, so we know that the A11 is going to be positive. And then we have this nice equation, which is R1, comma 2 to the n. Okay, so remember that the matrix is symmetric. So this guy is the transpose of this guy. So now we have two equations here, right? And they both indicate that this term is equal to 1 over R1 A1 2 to the n. So we can solve this this object, right? Because we found R11 before. And now we are left with this block here. Okay, we're left with this block here that we have to solve, and we know that this block should solve this equation. But now we can take this equation to be the step for the next factorization, right? So we can repeat step 1 for this subblock, and we can do this until we get down to the case in which this subblock is dimension 1, for which we will be able to solve with just substitution, okay? And then we back substitute back, and we get our factorization. Okay, so the algorithm works for positive definite A of size n, comma m. So here I will have to argue with you that in order to compute this block, we will have to again have a positive semi-definite matrix. But you guys, I think you guys believe me, because this block, this will satisfy the same properties as a positive semi-definite matrix. This is easy to believe. So the algorithm works for positive semi-definite A's of matrix n times n. So we take a matrix, then since it's positive semi-definite, A11 is greater than 1, and then we repeat this. Since the algorithm works for a certain dimension, it's going to work out for a dimension below, and then when n is equal to 1, the decomposition is complete. So let's take this example. So here we have the first matrix. We decompose this way. We have this expression. First of all, we find our beautiful R11 to be equal to 5, because it's equal to the 25. And after we do, sorry, I'm going a bit too fast, right? So this one here is here. So we write the decomposition like this. We have these elements. So we start by finding the first 5 and finding the first this first component. Okay, and this will solve us this part, and then we apply to the second row, right? So now we have this other row which remains with us. So the 18 is again we have to take the square root, so this goes to this object and blah 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 blah, and then this gives us this first equation where we have solved for the 3031, and we are just left with the R33. And the last elements, it's just a scalar, so you can solve it like this. Okay, so kind of sort of the classical recursive procedure that we have seen some other stage in class, right? So you fix one, you create a submatrix, and you keep repeating this. Okay, so why do we do this? Of course, when we do these decompositions, the first thing that we try to do is find matrix inverses. And solve a system of equations. So let's say that we're trying to solve a system of equation which is AX equal to B, and we figure out that A is positive semi-definite. Then what we can do is to decompose A as R transpose times R. Then what we can do is solve as following, right? So we solve first R transpose Y is equal to B. Since R transpose is lower diagonal, this is straightforward, right? So it's just a complexity of n. And once we've solved that, then we can solve R times X equal to Y. And this is an upper triangle, so it's backward substitution, okay? So the complexity of finding the solution becomes very, very easy. So the issue that now we have is that in order to prepare the factorization, we need 1/3 n to the cube, and then backward and forward substitution, they just have the cost of visiting the elements, right? So this is an n squared complexity. Very good. Okay, so this is very nice for us. Now let's complicate things a little bit. Suppose that B is an M times N matrix. So we leave the reign of square matrices. But let's just say that B still has linearly independent columns. So we don't want to have anything which is rank deficient. Then what we can construct is the ground matrix, which is B transpose B, which is positive definite. Okay, so depending on the relative values of M and N, we know that if we cannot have more eigenvalues than N, so we have to account for the fact that we could have some zero eigenvalues. So let's say that now we want to compute the Cholesky factor A given B. So we start computing A, which is B transpose B, which is the B square. Then we can apply the Cholesky factorization of A and find that A is equal to R transpose R. Okay. Then this partially solves our problem, right? Because then we still have to account for the fact that A is equal to B transpose B. Okay. So then we know that we can compute the QR factorization of B, which is going to give us this Q times R. So now that we have the A is equal to B transpose B, but B is equal to QR, so it's R transpose Q times R, and then Q transpose Q, we just said it's unitary, so it's equal to the identity matrix, and it gives us the R transpose R. So the matrix R is the Cholesky factor of A. So now we see the relationship between the QR factorization and the Cholesky factorization. So let's see some example here. We go for a tall matrix. I'm trying very hard not to say fat matrices because it discriminates against people. So I hope I stop saying fat matrices and say wide matrices. So B transpose B gives us A. We have this object. So the factorization of this object is just one step, right? Because it's simply 2 by 2. So the Cholesky factorization is this nice object, 5, 0, minus 1, 1. So then we can do the QR factorization, and we know that this is going to be the same term. And so we just have to find this object here, which is the Q version, because the R we found it from the Cholesky factorization. Okay, now we have two different ways of finding the R matrix. We can discuss a little bit of which way is the best way. So the QR factorization method is sort of stable, right? Because it doesn't require the squaring of the matrix A, right? So we know that the operation that we fear are inversion and squaring, right? Because if we square an element, the range could possibly either become much larger or much smaller, right? Depending if we have something which is very large, much larger than 1 or very close to 0. So the avoiding the squaring that we do in the factorization, Cholesky factorization, gives generally more numerical stability. But the complexity cost is lower, right? So B transpose B plus Cholesky factorization requires mn squared plus 1/3 n cubed flops. The QR factorization is m times n squared multiplied by 2, so it's heavier. So method 1 is faster, but only by a factor of at most 2 when m is much larger than n. Okay, so you see that this is the trick. Okay, now as we said in data science and in large data, big data analysis, right? Usually we have to deal with the concept of sparsity, meaning that we have these very large matrices, but they are only a few elements are said to be non-zero. So there exists an algorithm that factorizes dense matrices in 1/3 n cubed. This is the one that we just discussed. And this will take a few seconds for n up to a few thousands. Okay, but n up to a few thousand is no longer the standard for our machine learning algorithms. Our n can be of millions, right? Our n can be very, very large if n is let's say it's a gradient of an LLM, right? So these matrices that we are dealing with are much larger matrices in general. So if A is very sparse, then R is often, but not always sparse. Okay, so this is very desirable property. Then if R is sparse, then the cost of the factorization is much less than 1/n cubed. And the exact cost depend on n and the number of non-zero element and how the sparsity present itself. But basically, there are often very efficient algorithms for solving a sparse set of equations. So let's discuss now the sparse Cholesky factorization. If A is sparse and positive semi-indefinite, then it is usually factored as follows. So there is a permutation matrix P, and the role of the permutation matrices is to bubble up all the elements that are non-zero, okay? And then we have an R transpose and then R times P transpose, where P, as we said, is a permutation matrix, so it's only allows for it only corresponds to a reordering of the elements in the matrix A, because we want the non-zero elements to bubble up to the top, to be in the first K position. And then R is your upper triangular matrices, and we want the R to have big chunks of zero below the index K. Okay, so the idea is that we permute the rows and columns of A to factor as P transpose AP, which is equal to R transpose R. So the choice of permutation affects the sparsity, and there are different heuristic methods for choosing the number of permutation. So here you see some example of the sparsity of A, right? So here we have this, so you see what happens, right? So there is sort of this block of elements, right, that depends on many other variables, and this block of elements that depends on a subset of variables, and then this block of elements that depends on a smaller set of variables, right? So in a sense, what we want to do is that we want to take all these elements that they depend on each other and try to bubble them up at the top, so that then the width of this diagonal in which we find the non-zero elements become smaller and smaller, okay? And if you do a good job, then you see that the matrix becomes basically a bend diagonal matrix with some let's say out of diagonal elements, but it's very small, right? It's intuitively very clear that if we have to apply, let's say, Gaussian elimination in this case, then we will be able to save a lot of memory, for example, because we only need to keep a memory of the last variables that we solved, and so we don't have to store the full, let's say, few thousand matrices, few thousand values that we solve from the Gaussian elimination, so that the complexity of backpropagation or forward propagation will only be a constant. It will not be dependent on n. So that will allow us to remove a factor n from the complexity, and of course, this is a large, very large reduction in complexity. Okay, another example here. We see that the Cholesky factor, it's again this very bend diagonal. So if you factorize it correctly, then we only get this diagonal factor. Okay, so of course here there are many zeros that you don't see, otherwise this will not be possible. But it's clear that the solid blue hides a lot of, let's say, zero entries that they look blue simply because of the low quality of the image. But it's clear that let's say each row only depends on a few number of elements, so that if you reorganize it properly, then you have this bend diagonal structure. Very good. So let's say that now we have Ax equal to B, with B A in sparse and positive semi-definite. Then what we can do is that we compute the Cholesky factorization, and we have to choose a good permutation P. As we said, we mostly have to rely on heuristics in finding these good P's. There is no exact solution for this, right? So what we will do then is that we will permute the right-hand side with a P transpose. So we reorder the elements accordingly on both the left and the right-hand side of the equation. Then we solve R transpose Y equal to C by forward substitution, and then we do back substitution, solving RZ equal to Y, and then we just depermute the solution by saying that X is equal to P transpose Z. Very nice. Just a little bit of discussion of the complex matrices, what happens in the case. So in the case, the quadratic form, right, will involve this Hermitian instead of the transpose. And the quadratic equation will have this expression. So here we will have the norm, where we intend this norm to be on the complex L2 plane. Here we will have x conjugate I times xj, right? So the sign of the complex part is flipped. And notice that X Hermitian AX is real for all X that belongs to Cn, right? The complex plane to the power of n. So then the definition of positive definite and positive semi-definite remains analog, but instead of using the transpose, we use the Hermitian. The factorization now includes the Hermitian, and this is an upper triangular matrix with complex entries. Okay, just a bit of kernel method now. So we discussed the regularized least square model. Okay, so let's say that we are fitting the data with nonlinear parameters. Then what we can do is that we can add a regularization that penalizes the entry of the matrices. And this gives us a version of the least square problem where we have this penalty term for the magnitude of the gradients. And what happens next? We can find a solution using the regularized least square problem with this a to the minus 1. And then we want an algorithm to find this entries. So what we do is that we define Q to be equal to A times A transpose. And then we do the Church factorization for this. And this gives us an efficient algorithm for computing this. And then this other part, I'll leave it for you guys to look after. So should be okay. And I think I'll let this part for you guys to explore a little bit. I don't want to do the kernel method in class. I think it's something that you guys can see yourself. I rather move to something else. So just remember that this material is in the slides. Okay. So of course, so this is the application of a kernel method to the MNIST digital recognition. Okay, let's take a 4 minutes gap, 4 minutes break. I'll see you back at 10, and we move to some other topic. Okay, guys? Ciao, ciao. See you back in 4 minutes. Walk around, get some water. Hello guys, hello guys. Let's do something else. Let's do some non-linear least square, and then I'll let you guys go. Non-linear least square, be good. Bear with me, guys. 30 more minutes, and I'll let you go. As I said, I'm more interested from me presenting your material than going through the slides. I think it's not a good use of my time. I'd rather listen to you guys than talk. We'll do that next week, okay? Okay, some definition examples. So let's say that somebody give us a non-linear least square, which we define as follows. Right? We have a set of matrices Fi's, and what we want to do is that we want to minimize the sum of the Fi squares. And what we ask is for the Fi to be some differentiable functions of a certain variable x. Of course, it's a fairly general setting, right? So many different problems. You could equivalently express them in as a sum of squares of functions, right? So there are a couple of courses also in NYCU about optimization theory, right? And often the tricks they want us to learn in this type of courses is how to express problems in equivalent forms for which we have some efficient algorithms, okay? So I think this is an important exercise to do, right? And I think if you imagine, let's say, all sorts of problems that one can come up with, many of them, as a general statement, right? Many of them can be reconduced to the problem of minimizing the sum of square terms. Okay, so if we choose f to be an affine function, then ax minus b, right? So this is the function that we take. Then this will go back. This will give us back our linear least square. So let's give some example. So let's say that we have some unknown to the location or something, and we are measuring the distances to some known points. Okay, so you can imagine that you have multiple microphones, right? And each microphone is picking up the signal emitted by a certain element in the field, and the power is proportional to the distance through some coefficient, so you know how to find the distances. Then, of course, the nonlinear estimate will be to compute the position of x given all these type of measurements, and the rho will be the distance that you measure. The AI is the unknown position, and so the problem that we're trying to solve is the norm of x minus AI minus rho I. This will be the height component, and you want to minimize this term. Of course, if we take some other type of distance, if we have some other decay of the power, for example, we can all embed this into this setting. So let's say that now we take a correct position to be 1, 1. So this is the position of our targets, and we have 5 microphones, let's say, which are marked by the blue dots. Then the red square marks the nonlinear least square estimate of x in this position, and the x will be the you see this 1.18, 0.82, right? So the correct one should be 1, 1, okay? And then we have this object here. And what we do is that we plot here the line of equal value, right? So the function is clearly has a minimum in this point, although the minimum is pretty flat. Because we are sort of far away from the sensing points. And you see here that we have some sort of areas of confidence, right? So very far away regions are very unlikely. And also some intermediate point here, it's unlikely because the signal will have a very different profile if this were the case. So you sort of have an interpretation of, for example, this area, right? This area being the area with the same value for the minimum. Very good. Another classical example is a location from multiple camera views. So let's say that you have a certain intersection, you're trying to locate a pedestrian in a certain intersection, and you have multiple cameras on the intersection, then you will be given a camera model. The camera model is an A matrix, which is 2 times 3. Why? Because the 3D scene is projected on the 2 plane. So the A matrix A determines how the 3D scene is projected on the camera lens through the camera features and whatever location we have. Then we have B, which is a square, and C, which is an R cube. So our observation model is this one here, right? So this is the camera center. This is the principal axis of the camera, and this is the X in 3D. This is X prime in 2D. So the object location is the problem of finding the X which belong to the cube from the location X prime which belong to the square, knowing that the equation that relates the 3D position to the 2D position is 1 over C transpose X plus D multiplied by AX plus B. And these are all camera parameters, okay? C transpose X plus D greater than 0 if the object is in front of the camera, otherwise this would be negative. And this A, B, C, D characterize the camera and its position and orientation, okay? So this is 3D position and orientation, okay? Of course, this is a simplified camera model where everything is linear, and we love to operate in the linear domain. If there was, let's say, some lens distortion, as for example, you see in your camera lenses, which are very small, right? So that the camera lens is not infinite. Then you will have to have some correction of the camera characteristic before this, and then the location will go. Or you would say, well, if the orientation of the camera is in this range, and the object is in 3D space, then the distortion of the cameras are limited, so I can operate as if the camera is lit. Okay. Okay, continue from here. Then we want to set up this as a non-linearly square. So the option location X of the target is viewed from multiple cameras, right? So let's say that we have I cameras, and all of them they have the characteristic AI, BI, CI, and DI. Then for each of them, we have this relationship between the sensed point yi and the 3D position. And then the location of the 3D point is unknown, and we want to estimate it, and we want to take minimum least square, and this will be the equation that we have. Okay. And this is indeed how, for example, that perception of localization in 3D space is done in camera systems or in systems that use, let's say, LiDAR or infrared light, where the nonlinearities of the system are sort of minimal. So this is what we call model fitting. Is the case in which we have a certain set of measurement xi, and we have a world model which is theta, and we want to minimize the L2 square loss. So let's say that we have f hat x of theta is a parameterized relationship between the input and the output, where the parameters are the vector theta, and we have a p of them. Then we have a data set of points that are x1, y1, xn to yn. So the data set tells us the features and the labels, as we discussed already back in the beginning of the course. And what we want to do is we want to minimize the loss. The loss in this case will be an L2 loss. And we want to choose a set of parameters that minimizes this loss. And we found, if the model is parameter if the model is linear in the parameter theta, then we know how to do it. But in general, we will need to do a search over the parameters models. Okay, as an example, okay, let's say that we have the model that we have if f hat x of theta is theta 1 exponent theta 2x cosine of theta 3x plus theta 4. So this is a very strange model for the world, which is complex a modulated exponential, right? So we have a real exponent, we have an exponential function that multiplies a trigonometric function. If some of you has taken signal and system, you know that this is a complex exponential. So I was almost about to call it a complex exponential, but then I remember that some of you guys might have not seen complex exponentials. Anyway, so in this case, we are given all these green points as the dataset points. And what we want to do is that we want to choose the parameter theta, right? So that the observation is as close as possible to this to this parameterized damp and exponential, damp trigonometric function. And the way in which we measure the goodness of fit is through the L2 distance between the y hat produced by f hat and the true label y. So we set up a minimization problem where we have the sum of the dataset points of the label y hat, so the label predicted by our model f hat, which is a function of x and theta, and the labels, right, of the dataset points y. Another example is to minimize the mean square distance of the data points from the graph fx of hat. And for example, here we have a nice cubic polynomial. We have a set of observation, and we can, with this cubic polynomial, we have a data set, and we can, for example, if we take the classic L2, the classic least square setting, we take the distance between the dataset and the points on the y-axis only, but we can change this fitting to not be on the y-axis, but to be on the orthogonal distance fit. So we are assuming that there is a noise both on the observation and on the label. So what we do there is that we have to model the distance between the point and the curve, right? So here we will have this nice and beautiful graph, right? So we have the xi and the yi, and then we have the ui and the f hat of ui of theta, okay? So the distance is the L2 distance over this. So you see that we have a noise, sort of, right? As a noise, a distance on the x-axis and distance on the y-axis. And so we have a parameters theta, we have an optimization point, and we have a definition of the distance between a pair of points from the curve. So this one will depend on the gradient of the curve at a certain point, and then we minimize the distance square. Okay, so just another example of a regression problem where we take orthogonal distances between the dataset points and the curve, and the fitting curve. Another classic example that some of you might already seen, which is that one of binary classification. Now the dataset points that we have are binary labels. So we have a certain x and we have a binary label 0, 1. And what we're trying to do is that we're trying to guess, our model, right, is predicting whether a certain y label is equal to 0 or 1. But crucially, our dataset contains both zeros and ones. So we want the model to predict the likelihood of a label being 0 or 1. And then we take a hard decision, we take a hard threshold, or whether the label is 0 or 1, depending on whether the probability of being 0 or 1 is greater or less than 1/2. Okay, so in this case, we take the minimization to model. We decide to model the uncertainty of the label through using this sigmoidal function. So this is e to the u minus e to the minus u, e to the u plus e to the minus u. And this is a differentiable approximation of the sign of u. And the dataset points are xi, yi, and the yi is either -1 or +1. And crucially, we could have multiple values of xi that could have different labels, meaning that the same xi could have a portion of the label which is equal to -1 and a portion of the label which is equal to +1. And what we are doing with our model is we're trying to approximate the ratio of -1 and +1 in the data set. Okay, so gradients, right? So we said that we discussed this already partially. So let's say we have a differentiable function which goes from Rn to R. So we take a vector x and we spit out a scalar z. So what we want to define, the derivative of the function with respect to the vector input. And as engineers, we imagine our vector input to be a column vector, so that the derivative of the function with respect to a column vector would be a row vector. This row vector will be our nabla g of z, which contains in each position, right, the partial derivative of the function with respect to the xi. And once we have this definition, or we can, with definition of gradient, what we can try to do is to linearize problems. Okay, so we understand so much about linear function, and we really like the fact that we can solve linear problem very efficiently. That if somebody gives us a nonlinear problem, the first thing that we do is that we try to approximate the linear problem, the nonlinear problem with a linear problem using our beloved Taylor approximation. So let's say that somebody gives us this model G hat of X, which is nonlinear. Then the first thing that we do is to linearize it as partial derivative x1 with the x1 z1, partial derivative xn with xn zn, so on and so forth, which we can write in vector form as the approximation of g hat of x around the vector z will be the value of the function z, g at the vector z plus our nabla evaluated at z multiplied by x minus z. Okay, so same thing as the Taylor expansion, right? Notice that g hat is a scalar. So here we have a column vector times a row vector times a column vector, which is equal to a scalar. So this is really the analog of the Taylor expansion in vector form. Okay. Then we want to also define the Jacobian, right? So this is the operator d instead of nabla. So d of f of z will be the derivative of the function the function f that takes in input the vector x of dimension n and spits out the vector y of dimension m. So this matrix here gives you the nabla, right? The nabla operator of the first element of the output y. Okay, so this is nabla of y1 all the way to nabla of ym, and the ym is obtained as f of m of z, and the f of 1 is obtained as the y1 is obtained as the f1 of z. So you have a function that spits out the vector. What you can always do is that you can see the mapping from the vector input to one of the elements in the output as a separate function, which you call f of m, and then the Jacobian will be the nabla of these functions, okay? The stacking of the nabla of these functions. Remember that these are row functions, okay? And so when you stack them this way, you stack them you stack them as rows, okay? So now if we have a function with vector input and vector output, then we can have this linear approximation, this Taylor-like approximation on any dimension m and m that we want, and this will tell us that the approximation is equal to this f of z plus d, right? So now this is a matrix of the distance vector x minus z. So now we have to work out the dimensions, right? So this f of that is a column vector of dimension m. This again will be a column vector of dimension m, and this is a matrix which is m times n. We multiply by a vector which is 1 times n, so this is a vector of dimension m. So everything works out very nicely. Yeah, and sometimes we use the double notation, right? f at x of z, meaning that x is the independent variable and z is the point around which we define our Taylor approximation. So now we want to define we want to use this machinery, right? This Taylor approximation like thing in order to define what is a gradient for a non-linear least square. So we start from our matrix G, which we say is the norm of this matrix Fs. So what we want to do is that we want to take the derivative of G with respect to the xi's, right, to the vector of unknowns. So this gives this nice expression, because here you see you have a norm square. So this is still a scalar, right? So when we take the scalar derivative of this, we will have twice the partial derivative, right? So you see here 2 partial derivatives multiplied by the function. So this is This just follows from partial derivative with respect to xj, right? Then what we say is that, well, if we take the nabla of this function, then we are stuck in again the partial derivatives according to the partial derivatives from 1 to n, and then we put this inside here, and we ask what happens to the ij terms, right? So you see that this is derivative with x of j, we sum over the I, and then when you do a little bit of finagling, you realize that this stacking of the derivatives now gives you the 2 times d, where d is the Jacobian, and then we have fz transpose times f of z. Okay, so let's go back a second, right? So this is the g of x, and we want to find the derivative with respect to x of j, and then we want to evaluate this derivative as z. So now this is going to be a vector, because this is there are no independent variable left there, right? So we substitute z in all of this derivative, and we get finally this expression. And this is going to remember that this is a raw vector. Okay. So good, now we have an idea of what are the optimality conditions, because we know that even if we don't know how to find the minimum, at least when we are at the minimum, we should have that the Jacobian, the nabla, right, should be all equal to 0, meaning that if you look at the gradients, there is no particular direction in which you will want to move, right, because it's a stable point. You're in a stable minimum, because this is a square term, so we are in good shape. So what we do is that we can say that one of the optimality condition, or the necessary optimality condition, is 2d fx transpose f of x to be equal to 0. And this generalizes the fact that at the optimal point, then the derivative should be equal to 0. And then in general, this is only a desirable condition, because in the nonlinear case, of course, the fact that the gradient is equal to 0 does not guarantee that you are at the minimum. You have to add something on top. You have to add convexity, for instance. But we are working in the non-idealized case, when there is a problem to solve and we cannot decide that we need more conditions on the function, right? So if we have to deliver a product to a client, we cannot say, oh, well, we cannot guarantee you optimality. We don't know what to do because the function is not convex, right? So you just have to deliver a product. Okay, so we are in this optic now, in which we have to really find this numerical minimum. And the way in which we want to approach this is using this our beloved Gaussian-Newton method. So what we do is that we take a function, we linearize the function around a certain guess at time k, which is our beloved x of k. So remember that this notation means that we take the function, we linearize it on the independent variable x, and then we evaluate f x to the power of k. This linearization gives us the function evaluated at x of k, our current guess. Here we have our beloved Jacobian evaluated at the point x of k, and then here we have the difference vector, right? So we have the x minus x of k. X is still our independent variable, and x of k is the guess. And then what do we do is that we use this linear approximation to find the next x, right? So now this is linearly square, so we know how to find the x. And we say that this x that we find is the new guess that we have, and we repeat this operation until a few conditions are met. Either we reach a maximum number of operations, or this x of k doesn't change more than a certain relative error, let's say a 5% rule, and we decide when to stop. Okay. So now we have repeated this for k times, and we want to know what is happening. So if the Jacobian has linearly independent columns, then the solution has this nice invertible point, so everything is okay. And then we take a Gaussian-Newton step. So we say that the new guess is, this new guess is xk plus 1. We define the delta as the difference between the previous and the current. And then this delta takes this expression, which is which contains this inverse of the Jacobian matrix as evaluated in the point x of x, and this is a measure of sensitivity. Okay, so when you see this sort of inverse Jacobian many things in statistics come to mind, and you realize that this is a measure of sensitivity. Okay, so of course, for this inverse to exist, the function has to be the matrix has to be non-singular. But even there, we said, well, even if the matrix is non-singular, it's possible that the matrix has some eigenvalues very close to 0, which is not particularly desirable. Or the Lavenberg-Marquardt method. This is a variation of the Gaussian method. And we update that how to update and addresses how to update x of k when the columns of D of the Jacobian are linearly dependent. So we have eigenvalues equal to 0. We said that this creates issues when we want to define the inverse, because the inverse doesn't exist. So we have to invent a way of we have to resort to the pseudo inverse. So what we do is that we compute a regularized least square problem. So here we minimize the f hat, so upper linearized, multiplied by lambda, the difference between x and x of k. Okay, so then this contributes a term to our linearized version, right? And the idea of this term is that we want to penalize, right, the evaluation, right, from being too far away from the true value of the function. Okay, so if we see that the function changes a lot between its values at k plus 1 and its linearized version at x of k evaluated x of k plus 1, we want to penalize this. Okay, so this x, right, is going to become our x of k plus 1. So what we're saying is that if there is a big difference there, then we don't want this. We don't want this. So if the lambda is equal to 0, then there is always a unique condition. So it doesn't happen that that the Jacobian is equal to 0, because this has the effect of shifting the eigenvalues of the Jacobian away from 0 for a factor lambda. So this is always nice and desirable and introduces stability. So now we just see how this changes the final solution. You see that here you have the inverse again of the Jacobian, and you see that you have an identity matrix multiplied by lambda. Okay, so this is a positive semi-definite matrix. So it could have an eigenvalue in 0 or the eigenvalues close to 0, which are equally bad for us in terms of numerical stability. And what we can do is we can add this regularization, which is the effect of adding the identity matrix multiplied by lambda. So now if this matrix has a certain set of eigenvalues, adding the lambda plus the identity will shift the eigenvalues up, okay, of a factor lambda. So this introduces stability as it moves the eigenvalues far away. Of course, the price that we pay is that we are penalizing the function from changing a lot, so we cannot have very big steps. Okay, so it's possible that what we gain is stability, but what we lose is speed. And evaluating this Jacobian, it's very expensive because the matrix has size and square in some sense, and so it's numerically very it's very expensive to compute these terms. And when lambda k is equal to 0, then we recover the original step, which has this function. But when lambda k is very large, then the delta k will become 1 over lambda. Okay, so this will be a very small term because it's 1 over lambda k. Lambda k is large. And so you're taking very small steps. Okay. Very good. Then what we want to do is that we want to tune the lambda k so that we are not too fast and we are not too unstable, right? So that we know that if lambda k is too small, then we are unstable. If lambda k is too large, then we are too slow. So we want to, we want to sort of be able to tune this lambda dynamically. So as the iteration of the Newton method progresses, we want to be able to choose lambda at each step. And we know that this is sort of a reasonable price to pay because the lambda has this effect of adding an identity matrix to the Jacobian. So it's sort of just a local transformation of the diagonal elements, right? It's not, it doesn't introduce an unbearable amount of complexity. So what we can do here is that if we see that the progress is too slow, right, so that the solution is too close, then we can tune down the lambda so that we accelerate. And if it's too unstable, then we increase the lambda. So we can sort of dynamically choose the lambda as the iteration continues. Okay, good. So this is the method. Let's see the summary of the method. So we start by evaluating the linearized version of our sum of function squares. Then we compute the solution using the regularized least square problem around the linearized problem. And then we look at the value that we have. We decide if we should tune up or tune down the lambda. We can use the hyperparameter beta1 and beta2 to do this, right? So we can have this nice update. So if we need to tune up or tune down. And now we have the algorithm is controlled by these two hyperparameters. And in step 2, okay, this solution can be computed using the QR factorization, and we can terminate if the gradient is sufficiently small. Okay. And here we have different values of the iterates. So this is the minimization of the distance that we saw before. We can start with different starting points, and here we have different lambdas and betas and 1, and you can see how you take very large steps as you are far away from the optimal point, and then you slow down when you're here. This one here is also performing well, but this guy is just too slow, so it takes too long to this guy to approach, and then the algorithm will stop in some local minima because it doesn't travel enough the space enough, right? So this is the intuition that we have. This is the normal solution according to various choices of the parameter lambda. So you see the blue that is the one that goes close, right? The lambda gets close nicely. The red is more smooth, and the brown is the one that stops too early. Just the point here is that if you look at your residual, right? So the sum of the function square is what you usually call the residual. If you look at the sum of your residual, then you can understand a little bit how much your optimization has progressed, right? So if you see the red, you can be a little bit skeptical because you didn't see a very large decrease of the residual. But if you see your blue, then you've seen a lot of drop of the residual, so you're happy. And the brown is still further away, but you've also seen a large decrease of the residual. Very good. Okay. So now let's do a little bit more nonlinear equations, and then I'll let you guys go. Present. Nonlinear system equation, just conditional. Wait a second. Where are you? Sorry guys, just looking for my here, conditional linear Newton method. Okay. Share. Nonlinear equation. We go into presentation mode. Now we see the Newton method for the nonlinear equation, damp Newton method, and Newton method for least squares. So we saw before the nonlinear least square, and we said that we have this set of nonlinear equations. Now what we want to do is that we want to apply this to the solution of nonlinear equation. Okay. So the problems are very much related, right? Because if your sum of square is equal to 0, then it means that all of the equations are equal to 0. But of course, you understand that having the sum of square equal to 0 does not imply, it's like you don't force the sum of square to be exactly equal to 0. Then these equations are only satisfied in the sense that the functions are evaluated to something which is small. But we can see what happens if we want to find the solution of the equation exactly. So again, somebody gives us this n nonlinear equations, and they want us to find the 0. Again, it's a very general problem that you can try to solve in very many different ways. So you vectorize everything, you vectorize your x, and you vectorize your f, right? So now your f is a function that takes a vector of size n and splits up a vector of size m. Again, some example from resistive circuits. Let's move on. I'm not very good with circuits. So what you want to do is that you want, again, use this idea of iteration. right? Iterating over the Jacobian evaluation. So we saw before this identical step, right? So you have the next point, the next estimate of the solution is xk plus 1, is the current guess, minus the Jacobian to the minus 1 multiplied by the function evaluation. And you explain this equation by saying, if we linearize locally the function, then we can try to find the 0 in this local linearized approximation. This D is the Jacobian, so it's the derivative of the matrix of f at the point x of k. And then at each iteration, we are evaluating the function f, right? So there's a function evaluation and evaluation of this derivative, okay? So remember that this is, let's say, the n squared type of complexity, and this is only an n type of complexity. But of course, this is just a relative dimension, right? It's possible that the evaluation of the function itself, it's more or less expensive depending on the type of function that we are working with. For example, the f of x could be a sine, as it could be a solution of some very complicated integral, right? So we don't know anything about the function evaluation complexity. Good, but what we know is that we need to factorize this matrix D, this Jacobian matrix, right, in order to do this inverse, and we just hope that this is non-singular. So for the time being, let's just assume that it's non-singular. So the interpretation of the equation is that we are linearizing the approximation around a certain point, f of x. And you're using this, and once we have this linearized equation, then we solve it in order to find the next step, and then we repeat this recursively. So what are we doing here? So we have a function x. This is our linearized function, right? So we take an approximation that for small variations of the input, then we have a small variation of the output. This is sort of the meaning of our linearization. And this is an affine approximation. And the solution of the affine approximation is the following. So what is the relationship to the Gaussian-Newton method? As we said, here we're taking the sum of the function squares. So if this method goes to 0, then the x is also the a0 of the system of equation. What we do here is that we have fixed the m equal to the n, right? Basically, that's all we have done. Fix the m equal to the n. Because that's the only thing that we have changed. So if we apply, let's say, the Newton method to the function f of x, which is e to the x minus e to the minus x, and we start from x1 equal to 0, this is how the evaluation goes. And sorry guys, gosh, mousepad betrayed me. So this is the function. This is the value x, and this is the function. And no, this is the norm of the function f of x. If we take example 2, now we add this linear term, so we have this squiggly point, and here we can see the difficulty in determining a global minimum, right? So if our starting point is at -1, then we are trying to find a 0, right? So from -1 we are falling behind, right? We are falling at this crossing of the function. If we start from slightly past the point -1, then we find the point, we find this crossing here, and if we start by -0.7, then we stop at 0. Okay, so you see here, right, that we start from -1, 0.8, and 0.7. At 0.8, you might assume that you will find the 0 in 0, but for the way in which the step progresses, it's clear that the function skips over the solution in 0. And so just by changing the starting point by 0.1, we change our optimal solution from the 1.62, okay, so this point, to the 0 point. Okay? So notice that here we have 3 crossings. So for 3 different initialization, we get 3 different crossings. This is our sigmoid function. Starting point, yeah, so just finding the 0 of this function. So this is a much nicer function for which one finds a 0 because the function is very flat. But here the message that if you start from 1.1, then you go in the wrong direction and you never come back. Yeah, and some more examples here and there, not particularly interesting. So the method works well if you start close to a solution. Otherwise, you have no guarantees on the convergence. The dependency of the convergence on the starting point, it's a little bit disappointing, but what else can we expect? So the convergence, the convergence is usually expressed in this way. So let's say that we have an optimal point, which is our x star, and we can say that if our Jacobian is non-singular, then we could say that the convergence means that as x of k goes to infinity, x converges to x star, which means that the distance between the function the function minimum, the true minimum x star, and the current guess xk is less than the previous step by factor c. And this c is a way for us to describe the speed of convergence of the solution to the optimal solution. And here there is a quadratic term, or you can put any LP term. So if there is a P term here, then you will say that the convergence is of order P. P can be 1, so it will be linear convergence. For P2, we will have quadratic. For P3, we will have cubics, and so on and so forth. And so we want to be able to say, of course, the constant C is not always relevant, but what really happens is the type of exponent, right? We want to know if a certain algorithm converges to the optimal solution linearly, which is very slow, or, for example, quadratically, which is considerably faster. Okay. So again, we want to minimize the constraints. We have this function. We have a certain cost. We have optimal. We have local minima, optimal minima. We want to use the gradients. This is also called the directional derivative, and we want to follow the descending direction of this. Then, in order to know if we are going toward the minimum or maximum, we take the Hessian, which is the sort of the order 2 of the Nabla operator. So we take a partial derivative with respect to xi, we could take a partial derivative with respect to xj, and we stack it in a matrix of position n times n, so that now we can have this Nabla square operator, which refer to the Hessian, and in position xij we have this beautiful entry. And now when we do the Taylor approximation, as we did before, we can have the Nabla, and we can have the Nabla square. So now we can repeat whatever we did before, and this time we have an extra term, so that now our approximation is not to the order 1, it's to the order 2. We pay a price because now we are evaluating the Hessian and not only the directional derivative, but of course we can expect that we have a faster convergence. Okay? So this is the affine function. This is the quadratic function that we have, and then if somebody gives us this approximation, this order 2 approximation of the function, then we can find it. I can find it as well. Yeah, so if we have a function which is a sum of a function, then both the gradient and both the Hessian and the Nabla operator, both the Nabla and Nabla square operator are linear operator. If we have a composition of mapping, then we have this composition rule, right? So if we have adding a constant d, then this has no influence on our Nabla. But if you multiply by a constant, then this constant comes in front. Notice that when we have the Nabla square operator, we have a constant in front and constant in the back. Yeah, some example of a function here that we're trying to solve. Nabla square, gradient versus Hessian. So when we do the linear approximation, then we can use this quadratic term. And so convergence happens if the function is convex, and we can define the function to be convex in the higher dimension if we have that this Hessian is positive semi-definite everywhere. Okay? So if the function is always sort of convex, cone-looking in all possible dimensions, then this will give us a condition by which we know that we can converge to the minimum of the function. Okay, some example. I think we are very good. Yeah, I think this is just some nice examples for you guys. I'll let you go through this by yourself. I think it's fairly straightforward once we have seen what we've seen before. Not particularly exciting from the machine learning point of view or from the algorithmic point of view, So I'll let this topic for you guys. Okay, very good. So I'll let you guys go. I'll see you guys next week. Finally, we can hear your presentation. I'm sick of talking. We say hi to the people on YouTube that always follow us. Remember to subscribe, like, and ring the bell, whatever.